Finding domain and range of inverse functions. The outputs of the function f are the inputs to f inverse. So the range of f is also the domain of f inverse. Likewise, because the inputs to f are the outputs of f inverse, then the domain of f is the range of f inverse. And we can visualize the situation as in figure 3. So if we have the domain of f is equal to the range of f inverse, and the range of f is equal to the domain of f inverse. So that means if this is the input for f of x, there's your output. If this is the input for f inverse of x, then therefore that is the output. Now, when a function has no inverse function, it is possible to create a new function where the new function on a limited domain does have an inverse function. So, for example, the inverse of f of x is equal to the square root of x is f inverse of x equals x squared, because a square undoes a square root. Note that the square is only the inverse of the square root on a domain of 0 to infinity, since that is the range f of x, which is equal to the square root of x. Let's look at that on Desmos. Okay, so what they're saying here is that if I look at the square root function, okay, this is the square root function. Now, if I graph x squared, okay, what's happening here is that if you look at this piece here, okay, and now if you look at this piece here, starting at 0, 0 and going in that direction, that is the inverse of this one, if you cut this off, okay? So this entire piece needs to be cut off. So I'm going to show you this. I'm going to go ahead and copy this into our document here. Okay, so looking at this, I want you to again look at this question. It says the inverse of f of x is equal to square root of x is if f inverse of x is equal to this x squared, because the square undoes a square root. But the square is only the inverse of the square root on a domain from 0 to infinity. So what it's saying here is that the domain has to go from 0 to infinity. Okay, so what that means is I need to then restrict the domain by eliminating this part of the x squared graph. And so if I do, now you can see that they are inverses of each other. So you have to restrict the domain in order for that to work. And by restricting, what it's saying here is that we would say, okay, well, this function is an inverse, f of x is equal to x squared, as long as we know that x is going to be greater than or equal to 0, which means we have to cut this other part in half. And that's what they're saying. Now, we can look at this problem from the other side, starting with the squared, the toolkit quadratic function, f of x equals x squared, if we want to construct an inverse to this function. We run into a problem because for every given output of the quadratic function, there are 2 corresponding inputs, except when the input is 0. So for example, the output 9 from the quadratic function corresponds to the inputs 3 and negative 3. But an output from a function is an input to its inverse. If this inverse input corresponds to more than one inverse output of the original function, then the inverse is not a function at all. So to put it differently, the quadratic function is not a one-to-one function. It fails the horizontal line test, so it does not have an inverse function. In order for a function to have an inverse, it must be a one-to-one function. Going back to this graph, if we draw a horizontal line through the parabola here, which is the x squared, it's not a one-to-one function because it wouldn't pass that test. Now, if we come back up and look at that graph, if we eliminate the restriction, right, the left part of the graph, you can see that if we put a horizontal line through it, it does then become a one-to-one function, but only on the restriction. Now, in many cases, if a function is not one-to-one, as we stated, we can still restrict the function to a part of its domain on which it is one-to-one. So as we saw, we can make a restricted version of the square function x squared with its domain limited to 0 to infinity, which is a one-to-one function, and then it passes the horizontal line test. Therefore, it has an inverse. Now, if f of x is equal to x minus 1 squared on 1 infinity, then the inverse function is f inverse of x, which is equal to the square root of x plus 1. The domain of f is equal to the range of the inverse function, which is 1 to infinity. And the domain of inverse becomes the range of the function f going from 0 to infinity. Now, is it possible for a function to have more than one inverse? No. If two supposedly different functions, say g and h, both meet the definition of being inverses of another function f, then you can prove that g is equal to h. We have just seen that some functions only have inverses if we restrict the domain of the original function. In these cases, there may be more than one way to restrict the domain, leading to different inverses. However, on any one domain, the original function still has only one unique inverse.